Morning. Welcome to DVI Bushcraft and Survival. A little mini class on the theory behind mechanical advantage. So what is mechanical advantage and what do we use it for? Well, in the rescue world, we use mechanical advantage to haul a load. It's a force multiplier, right? So we can build out a system that will help us physically move a patient from one area to another, up or down a crevasse or a cliff. But rescue mechanical advantage is the same as mechanical advantage that we would use in the bushcraft and survival world. If we needed to haul one of our big game shoots, right? So if we have a deer and we have a really big deer, we're fortunate, we can build a mechanical advantage, a simple mechanical advantage to haul a load. So in any case, it's a force multiplier that has been used in the days since pyramid building. And we're going to go over a little bit on the whiteboard, and then we're going to get to making some that makes it easier to see. So mechanical advantage, we're going to use the word MA, the letters MA, to stand for that throughout the class. And we're going to speak about theoretical mechanical advantage and then actual mechanical advantage. Ideal mechanical advantage, I'll just put a note there. That is something that goes into a little more in depth on the basics of figuring out what our mechanical advantage is. So we're going to skip that and put that on another video. So theoretical mechanical advantage is just as it sounds. It's linear physics, but we work in a nonlinear world. So as we add items, i.e. friction, carabiners, pulleys, efficiency of pulleys, edge transitions for rope, the rope goes over an edge and there's friction. So friction is going to be an outlier that's going to change our theoretical mechanical advantage, right, in a perfect linear world, to actual mechanical advantage once we build out all the inefficiencies that are in the system. So it's a 3-to-1 is not truly a 3-to-1. It could be 2.7-to-1 based on the friction in the system. There's basically 3 different types of mechanical advantages that we're going to look at. First one is the simple. Next is a compound, which is a simple system built on another simple system that multiply. And then a complex system in which we have to use the method of counting units of tension. So we like to teach, unlike most classes, the most important, the hardest to understand out front. Counting units of tension is vital into building systems. It's also vital for the rescuer or the end-line user who's building a mechanical advantage to know what the system is rather than trying to memorize a pattern of ropes and pulleys, right? So everyone knows that if our anchor is here and our load is here, anybody that's dabbled in this knows if we tie our rope here and we pull on the load in this direction, that's a one person pulling a load. It's a 1-to-1, right? If I put a pulley here, that rope goes through the pulley and I pull downwards, it is still a 1-to-1 because for every foot I move of this rope, this line moves 1 foot, right? So far, simple, right? Simple 1-to-1. Importance of counting units of tension, and that's why we're going there first, is because in building a system, we can memorize this pattern. We can memorize a Z-rig 3-to-1, that it looks like a Z. But if we forget the Z pattern, or we forget the theory behind it, and we go to build something else, all of this is out the window. It's like trying to learn a word, how to spell a word without knowing what the letters are. So why is because this gives us the education and understanding in mechanical advantages that we can build anything from a simple system to a compound system to a complex system, knowing the theory behind it and not knowing how to memorize a pattern of ropes. All right, so the next component of this outside of ropes is pulleys. Pulleys are a force multiplier. They can count as a change of direction, whether they're fixed to the anchor, fixed on the load, or moving in the system. They are force multipliers, and that is very important to know. As we look at this pulley right here, our favorite ARS pulleys, you can see on this pulley, it shows a diagram. It shows that if I was to pull on this right side of this pulley with that rope, there's 1 unit of tension. We're going to count tensions rather than pounds for the demonstration, and then we can put in pounds that will show you the forces of where the load goes. So if I pull 1 unit of tension down, it goes through the pulley, it gives me 1 unit of tension coming out. It's a force multiplier. You can see that this is 14 kilonewtons. 1 unit is 14 kilonewtons. That now doubles at 28. What does that mean for us? And this is the most importance, is that now there is 28 kilonewtons of force onto whatever this pulley is affixed to. And if that's your anchor, we've now doubled our load. So let's take this to the board. Here's our direction of pull. Our load is 100 pounds. To get this to move 1 foot, I need to put in 100 pounds worth of force to move this 1 foot. If this was 100 pounds going in and 100 pounds coming out, because that's the equal amount of weight while this rope is moving through the pulleys, it's multiplying, it's a force multiplier. It multiplies this, splits it in half, but then is the force multiplier part is this now is 200 pounds. So this can be represented as the tension units. 1, 1, 2, out. Okay, we're going to build a 3-to-1, simple 3-to-1 mechanical advantage. The form is the Z-rig or Z-drag. Like I said, we're not going to memorize patterns of ropes. We're going to look at the actual mechanical advantage so we can build anything from here on in. So we always start off with the rope that we're hauling on, the pulling line. So that has 1 unit of tension coming in into this pulley. We have 1 unit of tension coming out. Since this pulley is attached to the rope, a hard cam, rope grabs, Prussics, hard cams, this is a plus sign. We're going to follow this up. 1 unit of tension coming in, 1 unit of tension coming out, puts 2 units of tension on our anchor. One in, 1 out, 2 units of tension to the load. This 1 comes down here. One plus 1 plus 1, or 2 units of tension here, 2 units of tension here, plus the 1 coming down, 3 to 1. There's a cheat at looking at mechanical advantages when they're in a simple way, not a complex. You can't figure this out in a complex way. But if we were to take away all our props, we can see that there are 3 lines leaving the load. It's being divided up in 3, therefore it's a 3 to 1. If there was 4 lines leaving the load, it would be a 4 to 1. If there's 1 line leaving the load and nothing else attached to the load, it's a 1 to 1. If there's 2 lines leaving the load, it'll be a 2 to 1. We're going to build a 2 to 1 next. In this configuration, you can see that the pulley is now on our load and not at the anchor. So it is no longer a change of direction. It is now a force multiplier that will create mechanical advantage. So using counting of units of tension, here's our haul line. As we're pulling here, there's 1 unit of tension. And then there's 1 unit of tension coming out. That means there's 2 units of tension on the load. That 1 unit of tension comes up to the end line knot to the anchor, which means there's 1 unit of tension here. 2 lines leaving the load. In the simple version, we can see that is a 2 to 1. What we can also see as we build these systems is what we talked about. Don't ignore the anchor numbers. So right now, theoretically, if our load was 100 pounds and we could pull 100 pounds, let's figure that out. There was 100 pounds coming in, 100 pounds coming out, force multiplied 200 pounds to this connection. That 100 pound comes up here and it gives us 100 pounds of force on the anchor. As we build these systems, you'll see that based on the configuration of where the pulleys are, whether they're moving or not, it will substantially increase the numbers and forces on the anchor. So if we had negligible anchors or needed to build out several anchors to actually move the load safely, we would do so. Okay, we're back to the 3 to 1. And we, in this configuration, if we're pulling up the side of a cliff or out of a mine shaft or out of an elevator shaft, pulling up might not be easy to do, right? Working over the hole is probably not the safest, easiest thing to do. So we probably want to have a high point anchor where we had a change of direction so we could be pulling in a downward fashion. Now what does that do to our system? Well, it's still a 3 to 1. As we can see, we'll do this. 1 coming in, 1 coming out. Puts 2 units of tension here. That hard cam progress capture device is a plus sign. 1 unit of tension coming in, 1 unit of tension coming out. Puts 2 units of tension here. Gives us a 3 to 1. All right. So we've added a change of direction. This, for clarity in the demonstration, we're not connecting this to the anchor quite yet, but this pulley would now be connected to this anchor and our forces will be applied to the anchor. So let's build that out. Just adding a change of direction to a 3 to 1, we count our tension units. 1 unit in, 1 unit out, 2 units of tension here, 1 in, 1 out, 2 units of tension there on our hard cam. It's a plus. Go back to this. 1 in, 1 out, 2 units of tension on this pulley. 1 coming back down, 2 plus the 1 is a 3 to 1. Still a 3 to 1, But look what happened to our forces on our anchor. We've now placed 4 units of tension instead of 2 units of tension on our anchor just by changing the direction of pull on our line. Let's count it out. 100 in, 100 out, 200 sitting here. 100 in, 100 out, 2 sitting right here. 100 comes up into this pulley, out here, puts 200 pounds here, moving right along. The 2 comes down to the 1 unit of tension here. It's a plus sign, it's a 3-to-1. Our mechanical advantage hasn't changed, but now we've went from 200 pounds of force on our anchor to 400 pounds of force. Okay, we're going to look at another configuration of a 3-to-1, and this is why it's important not to memorize a pattern in the rope. This is called a 3-to-1 Spanish burton. So if you can see, using the original tan rope, we have a changer, a 1-to-1 would have changed the direction, right? One line is leaving the load, and we're forces applied pulling on this out, still a 1-to-1, right? So if we're in a crevasse and we need more mechanical advantage than what we had on the system originally, say we set up and we said, hey, we just need to pull this from the overhead and to move the load, and then it's substantially more than we thought, or we're tired, weak, hungry, and we haven't slept for days, and we thought we had some gas in our tank, but there's none left. So with a small piece of cordelette, we can add a rope grab carabiner and a pulley to this, another rope grab, and now we will be pulling on the cordelette, and we'll start on where we're pulling from again. So again, this was a 1-to-1, but this is a Spanish burton, so it's classified as a complex line. Why? Because we're going to have pulleys that are moving as we are pulling on this system. So, counting our units of tension. 1 unit coming in to this pulley, 1 coming out. That puts 2 units of tension here. This now, 1 in, 1 out. This 1 here, 1 in, 1 out. It's 1 unit of tension here. Now we have to go back up here and count what's happening on the line that's being pulled by this 2-to-1. You can see this is a 2-to-1 pulling on this line. Now this line has 2 units of tension. That 2 units of tension comes up into the pulley, and 2 units come out, putting 4 units of tension on the anchor. That 2 comes down to this 1, 2 plus 1 equals 3, 3-to-1. So we turned our 1-to-1 into a 3-to-1 with a short piece of cord. But instead of applying 100 pounds of force up at the anchor, we now have 400 pounds of force on the anchor using the numbers 100 pound on the anchor and 100 pounds pulling. So we can bring that through the system, just to reiterate it: 100 pounds in, 100 pounds out, 200 pounds force here. That 100 pounds comes here, dead ends at the prusik, which is a plus mark. Going back up here, that 200 pounds of force is now being applied in and out of that pulley. It multiplies it, creates 400 pounds of force, comes down, that 200 pounds of force and 100 pounds of force is now a plus sign, so it's moving the load at 300 pounds of force at the load. We have to pull 3 feet of line to get the load to move 1 foot. But in a complex system, we have pulleys that are moving at different rates. So it doesn't work for a complex system. Another reason to know our complex systems and counting units of tension and what our pulleys are doing. Okay, so now we're going to be building a 5-to-1 complex. And it is complex in that it has pulleys that are moving. They're not on the anchor and they are not on the load. So they're moving pulleys, therefore we can't add them into the system as normal. We can't count the number of lines leaving the load because right now it looks like we only have 3 lines leaving the load, although this is a 5-to-1. So the only true way of figuring this out is to count units of tension. Now, why in the first place would we be adding a 5-to-1 to this? Well, we're in theory here, right? We have a 3-to-1, just like before, a Z, right? There's our 3-to-1. And all we did was add a rope grab and a carabiner with a pulley to this system. So three different pieces of equipment there. This is a pencil roll clip, so it's a carabiner and a pulley together. But with a simple having a carabiner, a rope grab, and a pulley set aside, we can change our 3-to-1 into a 5-to-1 pretty quickly. So let's go through the units of tension and how this works. So here's our haul line. We have 1 unit of tension coming up from our haul line, pulling from our haul line. And 1 unit of tension now coming out, puts 2 units of tension on our roll clip and our rope grab. Now we have something else going on here. So we have to follow this through. 1 unit of tension comes in, 1 goes out, which puts our 2 units of tension there at the rope grab. That 1 unit of tension comes up here, and since this is a rope grab, there's a plus sign. So our 2 becomes 3. Now there's 3 units of tension pulling through the system, through this pulley, out of this pulley, which now exponentially changes the forces on the anchor. It's now 6 units of tension on the anchor. Moving down here, this 3 comes down here to the 2 that sat here. It's a plus sign because there's a prusik, which gives us 5-to-1. We simply increased mechanical advantage to make our jobs easier. But what we did was substantially increase the forces on the anchor. So when we're adding mechanical advantage, especially in a complex way, it's good to know what we're doing. Again, don't ignore the anchor numbers because it's good to know what we're doing to the anchor when we're putting forces being applied, multiplied through pulleys in the system. I'm going to take these off so you guys can see a little better on what this looks like without any distractions. And then we'll go over forces. So, if our load was 100 pounds and we wanted to put 1 person on the rope that pulled 100 pounds, we would have 100 pounds coming in and 100 pounds coming out. That 100 pounds comes down to here and out there, which puts 200 pounds of force here. 200 pounds of force. That 1 comes up to here. That was 2. So that put 3 there. Right? 300 pounds of force now in our system. That 300 pounds of force comes back out of that pulley, but now places 600 pounds of force on our anchor. That 300 pounds force comes down to here. We have a plus sign because we have a prusik, our 2 and 3. Then now puts 500 pounds of force on the load. You can see just from a 3-to-1, we had 200 pounds of force on our load at a 3-to-1. Now it's 600 pounds by just adding one pulley and a rope grab. Substantially increasing our mechanical advantage, but also substantially increasing the stresses on our anchors. Next up is actual mechanical advantage. We spoke about theoretical mechanical advantage, and that's in the perfect world. Our pulley efficiency is 100%. Our pulleys are not perfect. Not even these awesome magnetic pulleys by ARS are 100% efficient. In actuality, so let's take a look at this pulley. If now our load was, instead of, it's 100 pounds, but instead of 100 pounds, only 90% is going into the pulley and 90% is going out. 100 pounds at 90% is 90 pounds. So 90 pounds in, 90 pounds out, 180 pounds on the anchor. Compared to before, where we had 100 pounds going in, 100 pounds going out, and 200 pounds on our anchor. You can see the pulleys, through friction, we lose efficiency in our mechanical advantage. On our anchor side, it's our friend, because it's applying less force to our anchor, but in our mechanical advantage, we're losing efficiency in the mechanical advantage due to pulleys. And this is going to come into play in our next shot. So let's take a look at our 5-to-1 complex using our 90% efficiency pulleys. We have 0.9 units of tension because we're losing 10% of the efficiency through the pulley, right? 90% efficient pulleys, we're losing 10% through the pulley. So 0.9 in, 0.9 out. That 0.9 comes down to this pulley, which also loses some efficiency. 0.9 out. 0.9 comes up to here. 0.9 and 1.8 puts now 2 units of tension, 2.7 units of tension here. 2.7 in, 2.7 out, puts 5.4 units of tension on our anchor. That 2.7 comes down to here, meets our 1.8 from before. 2.7 plus 1.8 is 4.5. So we can see that we lost some efficiency, and it's no longer a true 5-to-1. It's an actual 4.5-to-1 in the system. Now that's important to know because we don't carry unlimited amounts of kit and gear in the field. So it's great that we have 2 pulleys here that are very efficient pulleys. As far as pulleys go, 90 to 95% efficiency is a very efficient pulley. In the old days without ball bearings, pulleys were a lot less than that. But today we can pretty much figure that any pulley that we see that is from a reputable manufacturer has ball bearings, and it's a pretty efficient pulley, at least 90%. So if we had unlimited kit, this would be great. We'd have ball bearing pulleys on everything we have. But let's say we don't. Let's say we are missing a pulley and we decide to use a carabiner as a pulley, which we can do. What we know about that is that it'll work, but through friction, we're losing efficiency. this is where we're going to start to lose gas in our system. We want the most efficient pulleys up front. It's like gas in your car. This is an inefficient way to rig this, because right here we no longer have a 90% efficient pulley. We now are going into our initial haul with something I couldn't even tell you at this point, depends on the carabiner, but let's just call it 30%, 40% efficient. We're actually putting in 0.3 in and 0.3 out to start. So if we have one pulley and a carabiner in the system, we're going to swap these out so our pulley is closest to our haul line, putting better gas in the engine, right? If we put like we had here, this is starting out with bad gas. So if we swap this out, with a pulley, and we put our carabiner here, we're still remaining a 90% efficient, or 90 pounds in, 90 pounds out, 180 coming here. The other way around, it's 30 pounds in, 30 pounds out, and 60 pounds only being applied to this part. That 60 pounds then gets translated throughout the system, so it doesn't matter how efficient this is at this point, because we're losing all the gas as soon as we start to pull on the rope. So build out the most efficient parts of your system closest to the haul side, and then if you have to use a carabiner down here or a less efficient pulley, use it down here. Well, I hope that helped. A little understanding on mechanical advantage and why you should know how to count units of tension, how that's so important, and for memorizing the systems, just like any of you all that ever worked in EMS, fire, police, military, got your EMT. If you study exactly what's in the book, it's not applicable to in the field. It's not real world. You're considered a cookbook medic if that's how you work in the field, based out of a book. You need to know the skills and what it does to the body. Same thing in rope rescue. You need to know all the parts and components, and then you can build systems and don't have to memorize patterns and shapes, and it can be committed to your memory better. Like I said earlier, that's just like spelling a word. If you were to take a look at the word CAT, and you know that that shape C is a C, but you don't even know it's a C, and an A, but you know the shape of it, and a T, you know the shape of it, that spells the word cat, but you don't know what the C and the A and the T is, how can you spell anything else? You're just memorizing a pattern of shapes. And that's what people do with mechanical advantage. So we really want to stress, learn the theory of mechanical advantage, learn how to count units of tension, and be a player in the rescue biz. Thanks for watching us. We look forward to putting out more quality videos on all kinds of subjects pertaining to rescue, survival, bushcraft, communications, you name it, we're going to do it. We hope you enjoyed the video. Don't forget to like and subscribe. Appreciate you. Take care. Have a good day.